Okay. Let's look at something called a Latimer diagram. Latimer diagrams consider multiple oxidation states, and we're going to write them from the most oxidized state down to the least oxidized state. So we're going to write them in the sequence that you would see reduction potentials be written. Okay. What's the oxidation state on this manganese?
0.
And?
2 plus.
And?
3 plus.
And?
-4. No, +4, sorry.
Mm-hmm. Okay, so it's metal. Metals lose their electrons easily, so that's an oxidation, which means they leave behind a cation. So we're typically seeing cations. This is manganese 4 in the 4 plus 4 oxidation state. So when you write something and it actually has a charge, we use Arabic numerals and we write that it's a plus, or if it's an anion, we write that it's a negative. When writing out a chemical formula or giving something a name and incorporating the oxidation state into the name, things like, oh, this is awful, we can't have this anymore. Because no one knows, so us and ick mean more than, less than, but there's no number associated with us or ick. So you have to know something about the nature of copper before you can understand which one of these is that. So it's not really telling, it's not conveying to you the full possible information. So these are now called copper 2 chloride and copper 1 chloride. So if we're using it in a formal sense of this is the ion, go ahead, Arabic numerals, superscripted. But in the sense of I'm conveying the information to you in a less than, I don't know if it's formal, I'm going to use the word formal again today in a completely different meaning. I'm not sure that formal is the right sense for this, but that's 4. What's that? That's 6. And 7. So we can figure that out. Oxygen group 6, which means has 6 valence electrons. It's not going to lose 6 valence electrons to give it a closed shell. It will, however, gain 2. So I have an O2 minus, an O2 minus, an O2 minus, and an O2 minus. That gives me 8 negatives. And then I have a manganese that will take care of that. Now, what we're missing, because there's a negative left over. If you write the actual permanganate, you usually write the potassium out in front of it. It's always a potassium, it's never a sodium. It's not any particular reason. But that means that these 7 pluses don't balance those 8 minuses and that there is a net negative charge. Okay, so that's +7, and that's the highest oxidation state that we will see. Okay, we're going to measure some way, somehow, this versus this, this versus this, and find the reduction potentials for each of these steps. And I have those numbers written down, but I was just saying to Kat before we started, that the way I pulled this question, the way that this data was presented to me, I pulled this off the internet, is not the most usable way. Because this is common, that is common, that's common, that's common, and that exists, but this one is uncommon. So the most mysterious number that's going to go on the board is actually this reduction potential. And if I ever gave this question myself, I would go looking for this number. However, in the way that we're going to do it, that number is going to be given to us. Yeah, manganese, let's go look. Because our periodic table has common oxidation states written, and it says, oh, it says 7, 6, 4, 2, and 3, and the 2 is bolded. Why?
It's really common.
Why?
It's in 4s2.
Yeah.
Those come off.
It's going to lose both 4s electrons before the 3ds are even touched. So that periodic table says 6 is available. Well, I don't see very much 6. I see plenty of 4 and plenty of 2. Okay, let's throw some numbers in. So the numbers that are going in are standard reduction potentials. And they have a magnitude and direction. That is plus 0.56 volts and plus 2.26 volts and plus 0.95 volts and plus 1.51 volts and negative 1.18 volts. Comment on the magnitude of the numbers.
They vary, but they're similar-ish.
In what way do they vary but are similar-ish?
They're within a certain magnitude of
Okay.
0.5 to 0.2.
So they're bunched, aren't they? There's nothing that's outrageous there.
No.
Okay. It's not like 1 and 1 and 1 and 1,000,
Exactly.
right? Okay. What else? Is there an odd one out?
The zero oxidation state is negative.
Why?
Because it's easy to take off. We were talking, for us too.
Do we want reduction potentials to be positive or negative values? Okay. Which tells you. Remember delta G equals negative NFE. Okay, and we want delta G to be negative, right? So, without any other information, if you were to guess from a positive value of E, does the reaction want to go this way? And I know I'm going backwards and forwards with my finger, but that way?
Yes.
Yeah.
Yeah, because it's negative energy.
Yes. So 7 is a very, very high oxidation state. It feels some relief when you can reduce it. What about that step?
It's a lot of relief.
Yeah, so this tells me that 4 is a lot better off than 6.
It's about 3 times, right?
And there's another thing that we do in inorganic chemistry called it's gone. Diagrams, where you plot this kind of information, and you see where the peaks and the troughs are, and you say this element clearly likes to be in this oxidation state and clearly does not like Tanabe Saguna. Yeah, look that one up. Look that one up. This looks like a girl, and then that seems reasonable, and then it seems to like this one, and
You don't know why that.
not much of that in nature then. So we're not going to go out into the preserve and go on a nature ramble and trip over lumps of raw manganese. Would much rather be the ion. Okay. All right, that's first things. How about this?
It likes it. Really doable.
Yeah. Oh yeah. We said before, permanganate, that purple colored crystals, that solution, very, very high oxidation state. If you give it anything at all to oxidize, it will oxidize it. And if we perform that oxidation in acidic media, it tends to go all the way down to manganese 2. But if we restrict it by putting it in base, it tends to stop at manganese 4. So this is a very common reduction. How many electrons? It's a 3 electron reduction, because that's the 1, and then this is a 2. The question is, what's the reduction potential from here to here?
I want to add.
Yeah,
Okay.
we would all want to add, but no, because that is a 1 electron reduction, and this is a 2 electron reduction, and that makes them not even to each other.
Could you multiply the first one to get 2 electron and then add them together?
Could.
Is that right?
You could. What we're going to do is, we don't know, because we haven't been shown yet, whether cell potentials are additive. But what we do know, and you were in lab this morning when the chemistry 2 students were doing Hess's law.
Yes.
And what was the deal? Did you listen? What was the deal about Hess's law? Well, that's the calorimetry part. Q equals MC delta T. That's, they were measuring the heat exchange.
But yeah, you can add up endothermic, exothermic to get.
Enthalpies are additive. They're additive, that if I want to go from A to B to C, I can just add them up. And if I go from A to B to C to D to E to back to A, you add them all up, and they end up being 0, because you're back to where you started from. That something has to be exothermic and something has to be endothermic. So enthalpies are additive. Enthalpies. And enthalpies feed into that thing called delta G. And delta G is delta H minus T delta S.
Is delta S additive?
Yes.
Okay.
Do you remember that part when we said here is reactant, A numbers of A,
Yeah.
and B numbers of B,
Yeah.
turn into C numbers of C and D
Oh,
numbers of
yeah.
D. Okay, and then we went to the book, we went to the appendix, and we found all the enthalpies of formation.
Right, yes, yes.
Okay, and that the enthalpy of reaction was equal to the sum of all the numbers of the enthalpies of formation of all of the
Product.
products,
Oh, okay.
and you subtract from that the sum of all of the enthalpies of formation
Mm-hmm.
of the reactants. And because we could also do that
Yeah.
for the entropies, although we don't go changes, we go actual entropies. All the products. Right, okay.
Same.
When we looked in our general chemistry textbook, this was in Appendix D. And there was a column for delta H, and there was a column for S, and then there was a column for delta G. The delta G's were additive,
Yes.
and the delta G is the sum of all of the delta G's of the product minus the sum of all of the delta G's of the reactants. Okay, so this tells us that delta G's are additive.
Yes.
Now, we don't know if cell potentials are additive, but we do know that delta G
Yeah.
is minus NFE.
Ah.
So they are additive, not just the E. This whole term has to be additive. And we have to count the number of electrons exchanging hands. Okay, get it? Okay, so,
So you would multiply the first jump by
Yeah.
2 and then add them to the
Yeah.
second. Okay.
so we backtrack from history. We know from Hess's law that enthalpies are additive. We learned from Gibbs free energy in the later thermodynamics chapter that entropies and enthalpies are additive, which meant that the Gibbs free energies have to themselves be additive, which is really, really useful because
Yes.
it's just a predictive number. It's not a number in itself, it's just a predictor of the situation.
Yes.
Yeah, and it tells us spontaneity. And then we learned that Gibbs free energy was such a fabulous concept that we made it not just be delta G equals delta H minus T delta S, we made it be delta G equals negative NFE, and we made it be delta G equals RTL and K. So that we could apply it to all different sorts of things. Okay? So, we know that the Gibbs free energies are additive. Let's look at this one. I'm going to call this the reduction from 7 to 6. Okay. This is not a notation that I found in the book. It's just like, I'm going to write a whole bunch of things down and we're going to have to call them something, right? So, standard potentials, because they came from the appendix. The standard potential is plus 0.56 volts. So the delta G is minus NFE equals, how many N's? 1. And Faraday? 96,485 times plus 0.56 volts. And then the reduction potential from 6 to 4 is 2.26 volts. And so the delta G for this is -2. I wouldn't bother calculating it just yet because I have a feeling that lots of things are going to cancel. Times plus 2.26 volts. Okay. And because delta G's are additive, the delta G that goes from 7 to 4 is delta G of the 7 to 6 plus the delta G from 6 to 4. Because these are standard potentials, these also get to be standard. Okay. All right. You can either go ahead and put all the numbers in. Go ahead, do it. You can
That
no, because all you're doing is multiplying that by that.
Yeah.
Go put all the numbers in. Go put all the numbers in. Good. And then you have to find out what the difference is. Or you can say that this delta G is equal, because it's negative NFE. How big is N? 3. That E from 7 to 4 now gets to be equal to negative 1 FE from 7 to 6 plus the negative 2 FE from 6 to 4. Cancel, cancel, cancel. Cancel, cancel, cancel.
And if you
And E from 7 to 4 equals something divided by something else. Those F's that you could have included in your calculation, could have. Don't need to, because they're going to cancel. I get 1 times 0.56 plus 2 times 2.66. Divided by 3.
So when all the negatives cancel out, that's
Yeah.
okay.
Yeah, there's a little bit of rewriting and cancelling there.
I got 1.6
1.8.
No. What is it? I don't have either of those. 5.08.
Oh, it's plus, I'm sorry. Plus. 1.69.
I got that, yeah.
I'm a big fan of telling the reader that it's a plus, even, and not just saying it's a number, therefore it's automatically a plus.
Mm-hmm.
All right, so there you go.
Nice.
Could you do any of the others?
We could.
We could.
Do you want to do some of the others?
How about we do the one from and then 3 plus to 0?
Ooh, okay.
Just to.
That sounds like asking for trouble, because
Yeah.
you're mixing positives and negatives. I don't know what that answer is, but yeah, go ahead and do it.
Help me. Yeah,
And while you're doing it, I'll
We
see
have
if I
a-
can.
We just need those electrons.
Oh, I literally forgot you got that from up there.
Yeah.
Like,
So you've got a 1 and a 1 and a 1. I was reading an alternate source this morning, and the Nernst equation came up. And of course, not everybody uses N. Our general chemistry textbooks do, but the whole world doesn't use N for the number of electrons. Some people match the because that's a charge, that's a number that is associated with a charge, and we've been thinking, well, keep N for moles, which I really don't like that being a lowercase n here. Some people write that as a Z.
For electrons?
Yeah.
but then that feels like.
So Z is usually nuclear charge, which is usually the number of positives, but guess what? The number of positives is equal to the number of negatives, isn't
That
it?
makes no sense.
So yeah, just be aware
They're playing.
that you may at some point in your future see something as strange as delta G equals negative Z Fe,
Ew. No.
or
I really don't like the
It does
E
seem weird somehow.
equals E standard minus RT over ZF log concentration of something divided by concentration of something, usually reduced over oxidized.
Wait, what do we calculate?
The and then 3 plus to 0?
This one.
Oh, 3 plus, okay.
Let's go from here to here.
I think I got the number.
So that one, this one, because you've got a 1 and a 2, kind of feels like, oh look, it's weighted average. Isn't this one just going to be the straight average?
Isn't it also a 1 to 2?
From 3 to 2. Oh yeah, no, my bad. No, there you go. Yeah, there you go. Wasn't paying close enough attention. And while you're doing it, I'll see if I can find the actual value. I'm not sure.
Okay, no.
Wait a minute. Oh, and while we're at it, I can look up Tanabe Suguno
I
diagrams.
swear you made it up.
No, it's way, this is why I said this morning, you sit in the room after you've finished taking your exam and you do something else, because those things that you can't remember, while you're trying to remember them, will come to you when you're not trying.
That's so true.
So I always bring an alternate activity whenever I'm taking an exam.
Have you had other students who do that too?
No.
Oh, she's a physics.
I had a delightful student who, 4 or 5 years ago that sat right at the front of class and knitted. She knitted, crocheted, knitted.
Wow.
And students around her thought that was odd and impolite, but she listened to every single word I said.
Really?
She just needed something to do.
Oh, yeah.
This was so that she could sit still. And she was a fabulous student.
Wow. I wish I could pay
And
attention.
I'm wearing the socks that she knitted.
Oh.
I'm now Joe.
I was like, those don't look like they were knitted. Those don't look like it. Maybe I'm just crazy.
I can't see the socks.
No normal black clothes. Black clothes.
Just in the dark. Buying 20 pairs of socks each year on my birthday. And they all go in the pile in a drawer.
Yeah.
And over the course of the year, my dog chews holes in my socks.
Oh,
That's
perfect.
his expression of his love for me.
Of course.
And that's why I need new socks every year. But I have one style, and I never have to match.
Oh, that's good.
I got this as the answer. It's in grade school.
What you got?
Negative 0.283 volts.
Yeah, so we're mixing positives and negatives, which is always fraught with danger. Is it a negative number? Probably, because if it's hard to get from here to here, it's also going to be hard to get from there to here,
Yes.
right? And so this number is a negative what?
3.
3?
Well, what? From, wait,
Oh, negative 0.283.
yeah, sorry.
0.2.
I thought you were talking about the
That's what I thought
electron
it was
drop.
too, until he said what.
Okay. Let me see if I can find that.
You just need to see, like, how many electrons on that
Yeah,
arrow, right?
and I only realized because when you did that, it was like,
Oh, frost diagrams. What's a frost diagram?
wait, frost diagram, that definitely is cool.
You need to go look at my habits. You should know this.
You said this from Oaken, Dr. Moore?
No, no, from inorganic.
Inorganic. Frost diagram. And that was last semester.
Maybe they changed names on me. If we plot this information, not in terms of cell potentials, but in terms of delta G, but really, it's the same thing. No, actually, there you go. So, we're going to plot NFE versus oxidation state or oxidation number. And here's 0, and 1, and 2, and 3, and 4, and 5, and 6, and 7.
Why are you showing 0 on the electron instead of like underneath the X?
Because sometimes you have, I started saying it earlier, but I never finished it. Metals can be negative.
Okay.
The one that comes to mind is vanadium. Vanadium has, unlikely to be on our periodic table, vanadium has a -1 that is achievable. Now, here it says vanadium is predominantly 5, sometimes 4, sometimes 3, sometimes 2. There's a -1 as well.
And how
And
does that happen?
It happens when you have very strongly pi acid ligands. What's a pi acid?
I know what a pi bond is.
Wait, you said a pi acid.
Remember back bonding, back donation?
Oh, like the carbon monoxide?
Yes, exactly like carbon monoxide.
Oh, where you can draw from the.
So in carbon monoxide, the carbon has a lone pair of electrons that it donates directly to the metal, but then its pi star antibonding orbitals overlap with the d orbitals on the metal, and it siphons the electrons straight back out again. So it puts them in, but then it pulls them back out again through another path. That back donation pulls electron density away from the metal and allows really low oxidation states. So we can have complexes that have coordination spheres that are connected to multiple things and have an oxidation state of 0. And sometimes if you do it with the strong enough pi acid, you can go down to negative numbers. Vanadium does it, tungsten does it, ruthenium does it, rhenium does it. But mostly no. Mostly we're used to seeing metals.
So it's
here.
like carbon monoxide bond is better than carbon.
It absolutely is. Yeah. All right, here's 0, because sometimes those numbers are negative and sometimes they're positive. And when you are at the 0 oxidation state, you're on this line. And when you are below the line, you are stable. And when you are above the line, you are unstable.
They might be under a slightly different
Sugano diagram. You couldn't help yourself, could you?
That's so funny.
A Tanabe Sugano diagram. Oh, it's ultraviolet. They're the same shape as frost diagrams, but they mean a different thing. Yeah, okay, completely. Yeah, frost diagrams is what I was thinking. The Tanabe Sugano diagrams are the same shape, but they're to do with vibrational spectrum.
So I learned about that too.
Yeah. Yeah. So what we're looking for is the reduction potential from manganese 3 to manganese 0. Let's see if I can find it. 2 plus, no, that one's going to be just obscure enough that you have to go find it yourself. You both came up with the same answer.
Yes.
So I'm going to assume.
We did it right. We got it.
That is right. Yeah, that was never going to be found. Okay. remember cell potential. Now that we've jogged our memory and said that our cell potential is linked to delta G, and that's going to open up our world, because yeah, I could link it to thermodynamic values, but what's actually more important than that is the fact that these are additive, which tells me that they can be additive too. All right. What was the other delta G?
RT ln K.
Yeah. Now,
Was it negative?
that was my question. Because when I said it out loud a few minutes ago, I just blurted it out. Is that supposed to be negative?
I think so.
Yeah. How do we know? If we didn't know, if we couldn't remember, and we don't have access to a book, how could we convince ourselves?
A delta G has to be negative.
We want delta G to be negative.
So in R and T are typically positive, and
Yeah.
L and K is also typically positive.
Is it?
Well, if it's, I mean, whenever it's good.
When K is strongly to the right, then it's a positive value.
Yeah.
And when K is strongly to the left, then it's a negative value.
Yeah.
Okay. So if our value is going strongly to the right for a spontaneous style process, then this will be a positive number, and the ln K of this will be a positive number, which means that this whole term is positive, which would mean that delta G is non-spontaneous.
Yes.
So there you go. That's why you blurt these things out, and then you go, no, there's supposed to be a negative in there. Okay. So if delta G equals minus RT ln K, can we find values of K from cell potential?
Yeah, we
Yeah,
can.
absolutely we can. Erase. Wrong one. Let's use cell potential to calculate the value of K. All right. Delta G equals minus NFE, which equals minus RT ln K. And if you sit and you move things around a bit, I've got a constant and a constant and a constant, and then this log, which kind of takes us to half of what the Nernst equation was in the first place. So I want to have E on one side, and then move all of that over. N is a variable. F is a constant. R is a constant. T is a variable, but it's not going to move during our experiments. And if I say, please work at standard states, then I'm going to the whole lump of constants, natural log of K. And some people will leave it that way, and some people will go that the natural log is 2.303 of the log.
log of what?
Anything.
What?
Excuse
The
me?
log, the natural log of x is 2.303 times the log of x.
So that's the conversion factor?
Yes, just a conversion factor
Oh,
between
okay.
natural logs and regular logs.
Gotcha.
And some books will go term lnk. Our book goes term log k, which means this conversion factor is also in there. Don't screw your face up. It's a thing. People do it all the time.
I just don't like extra numbers.
Okay. So somewhere in here, E equals negative RTLNK over NF, right? Which is equal to negative 2.303 RTNF log K.
So the negatives stay even though both sides of them have a negative?
Oh yeah, look at that. There you go. You beat me to it. All of that scrunches down to a number. You've seen that number before. That's the 0.05916. We've seen that before.
Yeah,
right?
from the, okay, great. I was like,
If we picked up a different book, we have every reason to believe that that would be a natural log. And if it is a natural log, this would be a different number. Okay. All right, here's a question. Find the value of k. I have copper plus iron 3, what used to be called ferric iron, in equilibrium with iron 2, which used to be called ferrous iron, and copper 2 plus,
Dr. Wyatt,
which used to
are
be
you
called.
saying they dropped the, so when you're talking about the I's and the L's and all that, have they dropped that
Oh yeah,
convention
don't use it.
altogether?
Yes.
What?
Other than sulfuric acid, sulfurous acid,
And that's
nitric
the
acid,
only
nitrous
time?
acid, yeah.
I didn't know that.
For all inorganic salts, stannic carbonate versus stannous carbonate. Do you know what the obvious oxidation states of tin are? No. So don't use it. Okay. Ooh, we've got a couple of special cases. Is this a redox reaction?
yes,
What's being oxidized?
the copper,
Okay. What's being reduced?
the iron.
The iron is. Okay. There are a couple of cases, I'll have to pull one out, where you can. Oh, this is where the Frost diagrams come from. The Frost diagram tells you where my unstable ions are. Okay. And for manganese, it did this.
Yes.
Okay. So I have a stability here and an instability there. If you find a different ion that goes hump somewhere in the middle, you take that ion, it might split apart into two separate ions, one that goes lower and one that goes higher. That's called a disproportionation. And if you have a situation where it does this, those two might come together to make the stable oxidation state in the middle. That's called comproportionation. Disproportionation, comproportionation. See if I can pull one of those out for you. I'm sure vanadium's got something in there. It's regular redox. Okay, what do we need to know? We need to know reduction potentials. Okay. Now, one of these is already written as a reduction. The iron 3 plus an electron going to iron 2. Okay? And that value is plus. .771 volts. But that's not what's going on in the reaction. I have two of these, and two of those, and two of these. So this number stays the same. It's insensitive property. Okay. And my other, I've got copper being oxidized to copper 2 plus. So when I write this as a reduction potential, as a half reaction, that copper gains 2 electrons. So I've got 2 electrons and 2 electrons, and becomes copper in the 0 oxidation state. And its reduction potential is plus 0.339. Okay. Now, my next question is which one's the cathode and which one's the anode?
It's the cathode, the copper's the anode.
Because
The cathode is where the reduction happens, and that's what the iron is doing.
reduction occurs at the cathode.
Yes.
Red cat. Reduction occurs at the cathode. And this is a reduction. Okay, so when I try to find my cell potential for this, that is the potential of
The iron, the cathode.
the cathode. So they're both going to be reduction potentials, but the cathode goes first, which means where the reduction happens. And then I'm adding or subtracting?
Subtracting.
I'm going to subtract from that the reduction potential at the anode, which is where the oxidation happens, which means I take this number plus 0.771 and I subtract from it 339, and it gives me a value for the cell potential. Yep, okay. Done it? Oh, so,
We found E.
okay. So now, what are you going to do? So we've found the value of E that is going to go into this equation. E is plus 0.432 volts. N equals 2, it's a 2 electron process. All right. E is 0.0519 over 2 log to the k. So this is 0.432.
Wait, 500 or 591?
Oh, that's just me being sloppy. It's just me being sloppy. Okay. What if I took that 2 and put it over here? And I took that 0.05916 and put it over there, so that they are now equal to the log of k. If this term is equal to the log of k, then 10 raised to the power of that term is equal to k. I would not raise it to the power and then squeeze all of those numbers in. I would find this as a number first and then just put it up there. And you come up with a number?
4.02 times 10 to the negative, not negative, to the 14.
Okay, yeah, so also, always comment on the magnitude of your answer.
That's a real big K.
K is big and positive. What does that mean?
The reaction will happen. Yes. It goes to the side.
It is far to the right.
Which makes sense because our E cell is positive.
Yes. So when values of K are big, your E cell is a positive number, and it turns out it doesn't need to be a big number. Even small positive values of E cell. I'm writing it as a standard because it was our particular one is the standard, but it doesn't have to, it could just be under any general. Will generate big positive values of K. Okay. Units?
Not necessary.
Yeah. Yeah, we ignore the units. Okay, I brought some props.
Fun.
Things you've seen before, because we've got 2 kind of topics left. One's a tiny bit tricky, and then the other one is technical. And so this is a pH probe, pH sensor, or pH electrode, for a better term. And there's a little glass bubble. I mean, I don't know if you've ever looked. There's a little glass bubble.
At the bottom.
Yes.
There's a porous glass bubble, and we'll describe next week what's going in there.
It's protected by a plastic sheath so that our students can bang it around and it not get broken, because these are delicate. And this is a idiot-proof version. I mean, as idiot-proof as you can get. The good people at Vernier have made a sturdy one. What's left is a discussion about particular electrodes being used for particular tasks. And they're called selective electrodes. And we have, because we used to do a lot of water quality testing. An ammonium selective electrode. Oh, bugger. We'll just have to solder that back into place. This one has a different tip.
But
That's
just goes into solution.
Yeah, that's going to need a repair. And this is a nitrate selective electrode. The one that we don't have that we need to talk about is called the hydrogen electrode. And again, this just has a particular tip.
That goes here. And you stick this into it tells you right here.
That there is a water level. You stick that into a solution and it tells you you have this much nitrates in your drinking water. And the EPA regulates how much nitrate you're allowed to have in your drinking water. Story goes that in the 40s or 50s, somebody's child fell down a well, and by the time that they had excavated the well to get the child out, the child had died. And then they found that the water in the well had high nitrate levels. And like, bam, that's it. We got to regulate the nitrate levels. Whether that was measured correctly or the cause of death is immaterial. It has happened. And if you read food labels now, specifically for liquids, it will tell you the level of nitrates and nitrites that are in the product because they are federally regulated. So we'll look at specific electrodes, and then that we only have one day next week. That'll be Tuesday. Specifically, we need to look at the standard hydrogen electrode, and then maybe the calomel electrode, the platinum electrode, the pH electrode. Then we'll take a break, and when we come back, we'll do some more equilibria. We'll do complex equilibria. We'll do inorganic equilibria, or maybe even biochemical equilibria. We'll find something.
Or is it?